Okay, our first speaker of the day is Muyang Liu, who will tell us about towards realistic matter spectra in F theory. Take it away, Muyang.
Sure, of course. First of all, I'd like to thanks for giving me the opportunity to present our in-progress work here, which has been done in collaborations with Martin Beers, Miran Svetic, Ron Donaghy, and his student Mariana Ong. Okay, this work is motivated by a very important goal of string Vino. Namely, we want to construct a string vacuum whose effective theory reproduce the exact matter content of standard model particle physics. In particular, we need to fix vector-like pairs to accommodate the Higgs, and also to avoid exotic vector-like matter. Moreover, from a quantum field theory perspective, the vector-like spectrum are characteristic features of 4D vacuum. So if we understand more about the dependence between the spectra and the modular space parameters, it will help us to understand more about how certain theory behaves under the edge flow also. Among the all branches of string theory, I am personally interested in F theory because it is capable of, first, describing the strongly coupled type 2B string theory, including non-perturbative effects. And second, it allows us to translate physics concepts to geometric subjects in the elliptic Calabi-Yau fourfold. And last year, we managed to realize one co-Julian standard model constructions with exact chiral spectrum from the compactification. However, global F-theory compactification, the vector-like spectrum is hard to get from the topological data only, and thus raise our questions about how can we control this vector-like spectra in F-theory. I've started by explaining how to compute chiral and vector-like spectra in F-theory, and then I will point out that in realistic F-theory geometries, the spectra mainly depends on the appearance of Rhodes bundle. Of course, I will explain what is Rhodes bundle after several slides, so no worries about if you don't know what's the definition of it right now. And then I will introduce the so-called limited Rhodes constructions to figure out the global sections counting some those kind of Rhodes bundles. Subsequently, I will apply this method to explain how to count the global section countings in the realistic F-theory geometries and present an example about configuring exactly 3 generations of quark on a particular matter curves. At the last of 2 slides, I will present our future strategy about to find a complete matter spectrums in the F-theory, and also extend our previous database of the line bundle cohomologies to include the full gauge background data in the F-theory. To construct a standard model of physics, we need the following ingredients. First of all, we need a gauge group SU3 cross SU2 cross U1. And then we need 3 generations of matter particles, which is corresponded to the exact chiral spectrum. And then we also need 1 exact Higgs pairs, which sits inside the vector-like spectrum. With the above content, we can move on to talk about the coupling over the Yukawa interactions, the particle masses, and also their hierarchy structure. Beyond that, we can also talk about the physics beyond standard model, dark matter, dark energy, but those will not be my, the last line will not be my focus during the past study. Here, I singled out my contributions to the constructing standard model physics in the past, from the exact chiral spectrum to vector-like spectrum and also on Yukawa interactions and hierarchies. Let me first briefly review the F-theory of compactifications. It is described by a singular elliptic Calabi-Yau vibration. But in practice, we resolve these singular vibrations to a smooth waveform. And then the chiral metastates are represented by the vibrations over certain codimension 2 loci or the bases. If we turn on an untraceable field strength G4, which sits in the H22 of Y4, then we observe the non-vanishing chiral spectrum. So if you view from the Dirac operator, the chiral index is exactly the Dirac index, which is not changed upon the variation of gauge field, and thus is topological invariance. But their individual value is determined by the kernel and the co-kernel of the Dirac operator, and it's hard to determine by the topological data only. Here I summarize the past string constructions with exact chiral spectra. The first work on determining the spectra can be traced back to 1985, which is on the E8x E8. And moving forward, the number of massless chiral and chiral modes, anti-chiral modes, depend on F-theory equivalent M-theory three-form gauge potential C3, which we could use the Delinkl homology of this Y4 to interpret this C3 gauge potential. And this Delinkl homology sits into the following short exact sequence, where the J2 is the non-intermediate Jacobian and corresponds to the space of flat three-form connections. So it will have no impact on the chiral spectra, but will influence our vector-like pairs in the spectrum. However, the Delinkl homology is still hard to handle with, but we could use the Chow ring of the Y4 to provide at least a subset of parametrizations of the Delinkl homology, and it is much more computational feasible. Therefore, the full gauge data as elements A inside the Chow ring define line bundles LR over the meta curves, and the cohomology dimension of those line bundles count the vector-like spectrum, with the chiral modes counted by H0 and the anti-chiral modes counted by H1. Here I briefly list the challenges to determine HI. Although early this year, we present our large data progress results for the simple toric surface DP3. And we use the topological data to predict jumps of the vector pairs. And by comparing with the brute force computation, it reaches 95% accuracy. However, if we move into the realistic F-theory geometries, the computation is not allowed to do by brute force computation because the order of the complex structure reaches to 100 or even larger, and that exists our resources on the cloud machine. And also, it is impossible to get pullback bundle expressions of LR, which we easily to determined by which we could easily use the topological data to determine the H0 countings on it if the degree of the line bundle sits inside the applied regime of the Kodaira vanishing theorem. Hence, the jumps are hard to specify. Here I also briefly listed the past string constructions with the exact vector-like spectrum. It should be said that in the F-theory regime, the full construction of the vector-like spectrum in realistic geometry is not yet known. Now I want to present our latest progress about how to explicitly construct the globe section countings in realistic F-series geometry. We pick one specific constructions inside the covariant Sinan model 3 family F-series models presented by our collaborations with Jim and Tian last year. It induces a G4, the field strength in the following form. The terms sit inside the brackets. Luckily, the integral algebra cycles sits inside the Turing Z. But unfortunately, with the rational prefactor 3 over k bar cubic, well, k bar is the anti-canonical divisors of the base, the overall G4 leads to Turing Q, which will a liking of the method to handlers. Therefore, it is not a proper lift to the Turing Z. So we try to fix this lift by considering k bar cubic copies of the actual G4, and it induces a unique line bundles LR over the all matter curves. Therefore, the actual G4 induced LR subject to these conditions, such that the LR to the power of k bar cubic is equivalent to the curly LR, which sits inside the Turing Z. And we call that the straight LR is a special k bar cubic root of curly LR. That's what we call the root bundles. So we realized that the section countings of the root bundles is related to the vector-like spectrum in MSSM constructions. And moreover, on a genus J curve, there are n to the 2g power of nth root bundles L, which satisfy the following conditions, where m and n are all positive integers. Of course, they are not divided by each other. And if we pick specific F-series constructions in the realistic model, and the Y4 admits the K3 parameters as 18, and if we consider one particular line bundles over one particular method curve, the quark-doublet curve, the root bundle satisfies the following condition, such that L to the 18th power is equivalent to the Kc to the 12th power, where Kc is the anti-canonical divisors of the curve, which can be derived from the adjunction formula and then use the anti-canonical divisors of the base. Therefore, I conclude it is impractical to construct third root bundle on smooth and irreducible curve because it is not a pullback bundle expressions at all. But mathematicians realized that on nodal curves, it is possible to establish such so-called nth root bundle by the so-called limited roots. And I need to thank Mariella, also our collaborators, for pointing out this paper. The nodal curve is just a curve whose locally looks like x times y equals to 0. So it's a curve composed by two components, the x exercise and the y exercise, which meets at the origin. Here, for completeness, I present the root bundles expressions on a realistic F-series geometry. There are two types of line bundles classified by the genus of the meta curve, genus 10 and genus 82. On genus 10, the condition is simpler, and I will present example of counting 3 generations of quark on those type of curve. On genus 82 curve, however, the curve is much more complicated, and we are still towards to find such deformation to realize a realistic global section countings on those kind of curves, and that's also our Higgs curve set. Let me to mention that Y1 is the Yukawa point that meets by the 3 matter curves, the quark-doublet, the Higgs, and the write-down quark, such that the bundle expressions for the Higgs is composed by the pullback bundles and the non-pullback parts. First, let me pick a very special complex short choice to deform the original smooth and irreducible curve into another one. The curve, by choosing S3, equals to a monomial composed by each coordinates of the toric threefold. The curve chops into 17 smaller pieces, such that the whole curve is nodal. For completeness, I list the all curve components information here, and they are defining equations, the genus, and the degree of 2kc each ci. In the previous mentioned paper, back to 2004, mathematicians found there is a one-to-one correspondence between the limit nth root and the so-called weighted subgraphs. It means that we can construct a limited third root of 2kc by the following weighted diagrams. First, I draw those nodes to represent each curve component, and I also label the degree of 2kc for each curve components on by side. Second, we connect each node by lines. Those lines represent the intersection points that attach, for example, C1 and C6 here. Then I add widths on 2 ends of the line. There's a certain rules need to obey for those kind of weighted diagrams. Namely, the summation of the weights I add here must be 3, because we are looking for a third root bundles here. Then, if we look at particular curve component C1, I'm continuing to put the rest weights on it, such that after putting all weights, the degree on C1 is decreased. It is the original degree minus the summation of the weights I put here. And that obeys the second rule of the weighted diagrams. Namely, after all, the degree on the weighted diagrams is congruent to the original degree mod 3 here. So 6 mod 3 is 0, and 0 mod 3 is also 0. So the 2 rules of the weighted diagrams are all obeyed. Then I repeat the procedure above to place the rest widths on all curve components. And I also check if the 2 previous mentioned rules are obeyed or not. If they are not obeyed, then you are not finding a mathematic allowed diagrams here. Okay. Suppose there are ni weights attached to each curve component ci. Then the degree of the line bundle on ci after placing weights turns into the difference between the original 2kc degree and the summations of the weights here. So just to repeat, the procedure I do for the C1 here to the all rest curve components. Then I have computed the multi-degree each component after the above procedure, and that's their result. So if we divided the multi-degree by 3, we achieve the multi-degree of the third limited roots here. And we conclude that the number of global sections on the whole curve is given by the sum of local sections as followed. And notice that the H0 countings on the last 2 curves are fixed by applying the Kodaira vanishing theorem because their degree uniquely fixed the H0 counting on those kind of curve. So we are only left with the H0 counting as local sections on C1, which is degree 0 line bundles on genus 1 curve. Now I'm using torus diagrams to explain the 2 cases of the degree 0 line bundles, and they correspond to different local section countings. The degree 0 line bundle can be expressed by the 2 points on the torus regime. And if those 2 points, they are differed, meaning they sit on different positions of the torus regime, then we conclude that the divisors localized on this curve is non-trivial. Then it is associated to the vanishing local section countings on the torus. If we move the Q to the same position as Q, such that the resulted line bundle is trivial, then we conclude that the local section counting on it is 1. So we prove that there exists non-trivial line bundles on C1, such that the H0 countings on C1 is 0. And thus, it proves the existence of third limited roots of 2kc with global section countings as 3. And physically, it tells us that we realize exactly 3 generations of quark on these particular matter curves. And here I present our future strategy, such that we anticipate the F-series MSSMs with the exact vector-like spectrum could be constructed for a combination of those root bundles from the following steps. First, we pick a very special, but still physics variable fourfold y4 tilde, in which we could deform the Higgs curve into nodal, and we could find limited roots on these nodal curves, which H0 contains being 4, such that we accommodate exactly 1 pair of Higgs. And we are still looking for such special geometries right now. Then, for the rest of matter curves, we artificially deform them out of the physics variable fourfold geometry y4 tilde. And we also deform those curves into nodal curves, such that we can apply my previous procedure to construct roots with H0 counting as 3. And then, by applying upper semi-continuity, H0 remains constant when tracing those roots back to the original smooth generic curves. And we argue that that's the complex structure of the rest curve when we sit inside this special physics fourfold geometry. And then all other curves admit roots with H0 equals to 3. So if the above procedures are satisfied, And then we said such y4 tilde exists. Then we conclude we find MSSM with exact vector-like spectrum. Phase 2 of our book, we still need to include the choice of spin bundle to fully specify the line bundle. And second, we need to interpret the freedom of gauge background encoded in the intermediate Jacobian. And we are planning to extend to construct a database of Y4 tilde, admitting exact vector-like spectrum of MSSM, and also including the above full gauge background data. And we are planning to add those extended database to our original line bundle cohomologies database working on the simple toric surface. And that's all I want to talk today. Thank you.
Okay, thank you, Muyang, for the very nice talk. Let's all thank Muyang using our clap emojis. It looks like Herb has the first question. Herb, do you want me to read it, or do you want to say it?
You go ahead and read it.
Okay, cool. Yeah, have you considered models where a reducible matter curve has one smooth component of genus higher than one and the rest are rational?
You mean that you chop the curve into one rational curve? Oh, sorry, into one genus, one curve, and the rest the curve are rational curve?
That's right.
Yeah. Yes, you can also apply our limited rules construction there. That's what we did. Recall that's the genus information of our matter curves here. So if you
I see. I didn't understand that. The genus is the subscript on the curve.
Oh, no. The genus is not the subindex of the curve. The genus is listed here. We use 1, 2, 3, 4, 5, 6 to label the curve. That's it. There's no information.
Yeah, I need to move the chat box here or close it so I can see that slide.
Oh, sorry.
Yeah, so but my question is, I see that slide, but there the genus of all the components of the matter curve is 1 or 0.
Yes.
Yeah, I'm asking if you've also considered models where one of the components is genus higher than 1. In other words, that carries more cohomology and the others are 0.
Yeah, that's also doable. But if the degree of the weighted diagrams on those higher genus exists the applied regime of Kodaira-Wanxin theorem, then we don't know the then the astronaut countings on it is not uniquely fixed. We need to apply further computations to make sure how the local sections on this particular higher genus curve is.
Right, but so, I mean, the line bundle may have deformations where the H1 vanishes, for example.
Exactly. So if you manage to find the weighted diagrams, as I present here, and you find that after taking the consideration of the vest here, the resulted degree, make sure that H1 vanishes, yes, we can also enjoy the results from this higher genus curve. But unfortunately, we haven't found such weighted diagrams if we consider those kind of setups.
Okay, yeah, I'll pursue this by email then afterwards. Thank you.
Sure.
Okay. If there are no further questions, let's thank Muyang one more time for the very nice talk.